This video is part of the chapter competition in the course Evolution of Plant Interactions at the Ostrava University. When plant growth depends on two or more resources, these resources can interact with one another. Based on their interaction, we can classify two resources as essential or substitutable. Two resources are essential if they're both required for the plant growth and one cannot replace the other. This is the case, for instance, with phosphorus and nitrogen. Both are absolutely necessary for plant growth. Nitrogen is used in amino and nucleic acids, and phosphorus is used for the production of nucleic acids. There is no way one of these resources can substitute the other. Alternatively, two resources can be substitutable. When one resource is scarce, it can be replaced by the other. This is the case of different forms of organic nitrogen, such as nitrates and nitrites. They can be both used to acquire nitrogen via different metabolic pathways. Previously, we saw how population growth changes in response to the abundance of one resource in its environment. Let's see what happens when we have two resources. Representing the relationship between plant growth and two resources requires a three-dimensional plot, which is difficult to analyze. But there is a very neat way to visualize this relationship with plot called isoclines. An isocline plot is informative about how the population growth rate will change if the resource level in the environment changes. These growth isoclines are equivalent to topography isoclines on maps. The plot axes correspond to the amount of each of the resources. The actual isocline corresponds to a combination of resources for which the population is at equilibrium. It neither grows nor reduces its size. Compare this to a topographic isocline. If you're walking along the blue line on the map, you will be going neither up or down the mountain. The resource isocline here is typical for two non-substitutable resources. The line never intersects with the plot axis. So the x-end of the isocline can give us the limitation level of nitrogen below which the population cannot grow because it doesn't have enough of the resource. Similarly, the y level of the isocline gives the limitation level of phosphate. If the population supply of resources is below the isocline, this means the population lacks one or two resources, so its growth will be negative and its size will decline. In a similar way, if you're headed below the isocline on the mountain, you are headed downwards. For instance, on the high X end of the plot, the population has plenty of phosphate, but not enough nitrogen. And because the resources are both essential, non-substitutable, it cannot grow. On the high Y end, the population has plenty of nitrogen, but not enough phosphate. So again, the population declines. Close to the plot origin, the population lacks both nitrogen and phosphate, and therefore cannot grow either. But if the resource level are on the other side of the isocline, then there are sufficient concentrations of both phosphate and nitrogen and the population can grow. This is the same way as if you're headed up the mountain, you are in the orange zone delimited by the isocline. The isocline of two perfectly substitutable resources, contrary to the essential resources, intersects the plot axis. In this case, one of the two resources can be completely absent, but the population will be still able to grow if there are sufficient amounts of the other resource. For instance, this environment has no nitrate, but it still has sufficient levels of nitrate to sustain its growth. And the inverse is true in this environment. Only if both the concentrations of nitrate and nitrite are below the isocline will the population growth be reduced. In reality, very few resources are perfectly substitutable, and instead they have either a synergistic, positive effect when they're combined, or an antagonistic, negative effect when they're combined. Complementary resources have positive synergistic interaction. When the species uses both of them, its growth rate is accelerated compared to when it uses only one of them. This is shown by the concave curve. If you compare it to strictly substitutable resources that have a linear relationship, you see that there is a whole range of resource combination for which the plants grow better if the resources are complementary. Antagonistic resources, on the other hand, can have a negative effect on population growth when consumed at the same rate. Again, compared with the strictly complementary resource relationship, there is a whole range of resource combinations for which the populations grow worse than for strictly substitutable resources.